right, good morning, students. This is going to be the last chapter, actually, or last chapter, pretty much, of Earth science. So let's just get right into it. This is all about geologic history, and we're going to start with relative age dating. What is relative age dating? In the next lesson, we'll compare this to absolute age dating. So we'll do both. What we're looking at here is actually it's a really nice picture. It's pretty clear of if you could guess it, sedimentary rock layers of varying thickness, and a general rule when you're looking at sedimentary rocks like this is the older rocks are on the bottom, the younger rocks are seen on top, and that comes from the law of superposition. So, the Grand Canyon, for instance, layers of mostly undisturbed sedimentary rock of different composition. We got some shale, some sandstone, some limestones, towering up. If you've ever been to the Grand Canyon, you definitely know how incredible it is. And yeah, because it's undisturbed, it's just deposited layers one on top of the other. The rule is older rocks are on the bottom, and younger rocks are on the top. And a big reason why that's true is, because of another principle, the principle of original horizontality, that, all sediments, and eventually when those sediments become rocks, they're first deposited flat. So for the most part, if you're seeing, flat sedimentary rocks, unless there's something else going on, for the most part, that's how they were first deposited. That's how they were formed. So if you see any tilts, if you see anything else, you know that they've been disturbed, and that is not part of the principle. But the principle of original horizontality is that all sedimentary rocks begin as flat surfaces. Now, this is how you disturb rocks. So when we talk about undisturbed layers, well, this is disturbing the layers. You can fault the rocks, you can cut them, right? Earthquakes can cut things, stress builds up and the earth cracks. You can get folds. A good analogy of that is like in these towels here. You can see how they were layered, and we kind of push them together, and it creates these really nice folds. And rocks can actually do that. So here we have some really nice folds. It's hard to tell exactly how big this is, but these would be whole mountains. So these are whole mountains here, and if we look deep inside the earth, what we see is actually the rocks themselves have been folded. This is what it looks like in real life. This is one of probably my favorite pictures, I think, of like all time. It's this incredible mountain fold. We're really far away right now, right? These are all trees. So we're very, very far away. You can just see how the sedimentary rocks here are just curling up, and they come back down, and then they're curling up again to form this mountain range. Just really magnificent. All right, faulted rock layers. I just want to show you an example of how the law of superposition would not work here. Because again, the law of superposition only works with undisturbed rock layers, and these have been disturbed. So for instance, if you were out here doing some geology stuff and you wanted to relative age date this area, you might say to yourself, okay, well, these rocks are on top, and the rocks I'm standing on are below it. Oh, well, these rocks here must be younger than these rocks. Well, no. You would have to do further investigation and realize, wait a second, there's a fault here. These rocks and these rocks are actually the same age. You would actually have to figure that out. So, disturbing rock layers, the law of superposition doesn't work as well. You can also tilt rocks, so you can see how these layers here have been tilted. We see more tilting, we see faults, we see this huge red thing here. We'll talk about that in a minute. All right, so an unconformity. Let's just keep going. So what is an unconformity? Well, it's preserved evidence of erosion. So what does that mean? Well, let's kind of go over it. So let's say we have these 4 layers here, and they were deposited over a long period of time, and now we have mountain building. There's some kind of convergent plate boundary, continents are colliding, and now we've bent the land. Over a long period of time, that those layers will get kind of shaved away, right? Water, wind, ice, erosional forces, weathering will destroy the rock layers over millions of years. And you can see now we have these mountains here. Okay, this is the surface of the earth. Even more time goes by. Look what happened. Now we have sediment being deposited on top of that. Well, there it is. There's our unconformity. We have a preserved evidence of what was once erosion in the distant, in some time in the distant geologic past. And when we say geologic past, we just mean extremely long periods of time ago. That's what geologic past pretty much means. Here's another example. We have these rock folds. It's kind of the same thing. Rock folds here, and they get shaved away, and this is what's left. So it's up to a geologist to attempt to reconstruct and reimagine what the surface used to look like before the unconformity. In rock layers, especially in a picture, it's a squiggly line. So there it is. We have kind of our squiggly line. That's evidence of past erosion. It's called an unconformity. This is what it looks like in real life. I took some of these pictures. This one I did not take a picture of. You can clearly see this fold here in the sand. It looks like sandstone. And then there's like this, line here, and then new rocks on top of it. That's the unconformity. How about this one? This one's really incredible. We have these beautiful rock folds that are huge because this person down here is for scale. So you can see how big these rock folds are. Not nearly as big as the other ones in the mountain, but still quite large. There's the unconformity because we have these horizontal layers on top. So this was eroded. All of this was eroded away. All right, this one I did take a picture of when I was in graduate school. Even in, when I was getting my bachelor's degree. We did so many of these road trips. We'd go out there, check out rocks. We learned about things in the classroom first, and then go outside and actually look at real examples of it. It's pretty amazing, and it's really fun too because you're outside. As long as it's not raining or snowing, you're fine. So here we have the Grenville Gneiss. It's 1 billion years old. And over here we have what's called the Hardyston Quartzite. These are just the names of these particular rock units. And then you can see the difference in age. There's a huge difference, and they're right next to each other. Well, how can that be? Well, there has to be an unconformity. This is 540 million years old, and this is 1 billion years old. Well, where's all the time in between? Well, it's gone. It's been erased. It's been eroded away. So this is a good example of unconformity. This is probably my favorite unconformity for a couple of reasons. And we can actually go to it, digital or virtually rather, virtually. So can I get this to be full screen? Yeah. All right. So we are in Alexandria Bay. That's all the way upstate New York. It's not too far from the Canadian border. I want to say it's by the St. Lawrence River. So we're really far up north in New York State. And what you're looking at are a bunch of rock units. And I can zoom in pretty far or pretty close. So I'm just going to show you what we're looking at here. This is pretty incredible. This is one of the most famous unconformities in the world, by the way. It's called the Great Unconformity. And the reason why it's my favorite is because this is actually where I collected my first 2 rocks ever. And I was 18 years old. And I have some more fun stories about my time out here. It's like really burned into my mind. So down here we have gneiss. This is all metamorphic rock. You can even see what looks like some tilting here. If there were past sedimentary layers, or these are probably foliation layers here. This is all gneiss. It's a billion years old. And you can see like kind of a line here. There's a line. You can actually crawl into there. I never did do that. But you actually could crawl into there. And then right above it, I'm going to zoom in because you can really zoom in quite far. This is a gigapixel image. You can see these clear layers. This is called the Potsdam sandstone. And it's a sandstone. So we have gneiss, a metamorphic rock, and then we have on top of it a sandstone. But the difference in age is incredible. And it's actually about the same as the other rocks we saw. It's not too far off in terms of the age difference. So the Potsdam sandstone is about, again, the exact figures I'm not really too concerned about. About 500 million years old, early Paleozoic. And this is Grenville, a billion. So the amount of time in between these is incredible. It means that 500 million years of time or rock is missing. Hence why it's called the Great Unconformity, because we're missing so much rock. We're missing so much information about what was going on during that time, at least at this location. This location did not preserve any of that. All right. The principle of cross-cutting relationships. So let's just go over that. It states that a geologic feature that cross-cuts another is always younger. So for instance, let's look at this geologic feature. Here we have a cut, a fault. And this fault, you can see, it cuts through everything. It cuts through A, it cuts through B, it cuts through C, and it even cuts through this feature here, D. So it cuts everything. That means it's the youngest thing, meaning it was the last thing to happen in this area. And part of, and I guess using all of the principles that we've learned now, superposition, the principle of original horizontality, and the principle of cross-cutting relationships, we can now start to figure out the sequence of events in this area. So we'll do this one, I'll do this one for you. So for instance, what happened first? Well, C happened first. This rock layer C, it was deposited first. Why? It's on the bottom. That's the law of superposition. So C happened first, then B, then A. That's easy, right? Because oldest on the bottom, youngest going up top. Fine. Now after that, we have D. D comes later, and we know that because it cross-cuts C, B, and A. So D has to be next. That's the next thing that happened. And like we said before, E crosses everything. It's part of cross-cutting relationships, so it must be the youngest thing. So in order from oldest to youngest, C, B, A, intrusion, D, this is a magma intrusion. Liquid rock was injected in and it froze in place. Okay. Here's another one. Okay, we have a bunch of rock layers here. We have an intrusion. Oh, we have some contact metamorphism. We learned about that a long time ago. Well, not that long ago. So what's the order of events, right? Well, according to the law of superposition, E comes first because it's on the bottom, D, B, A, and the last thing that happens is C, because C crosses everything. You can see C, all this, this whole intrusion here, it's crossing into everything. So it must have happened last. Okay. Continuing with this idea of intrusions. Okay. So if we analyze these rock layers here, you might say to yourself, Well, the youngest on the bottom, that's easy. F, that's the oldest. And then E comes. And then you might say C, B, A, and the last thing you might say is D. But here's the problem with that. D is not an intrusion. It's actually an extrusion. So let's go over how that works, because that's not straightforward. If you notice here, there's only contact metamorphism along the bottom of this rock unit. There's only contact metamorphism on the bottom. There's no contact metamorphism on the top, which means that C didn't exist yet, or CBA for that matter, did not exist yet when D happened. Which means that when D came in, it was an extrusion, meaning it was some kind of volcano erupted, it spilled onto the Earth's surface. The Earth's surface used to be E. D came up as a liquid, spilled out, it contact metamorphosed the bottom layer, but there was nothing on the top layer because the top layer didn't exist yet. So according to this, the order is actually FED, CBA. And the way we remember that is if there's contact metamorphism on the top, it's an intrusion, because that means that C was there. So it's an intrusion. If there's no contact metamorphism on the top, it must be an extrusion. Here's a good example of that. You can see how H, this is clearly an intrusion, and it has contact metamorphism on the top and the bottom, so it must be an intrusion. Now this one's really complicated. If you want to pause the video and try and figure it out by yourself, what is the order of events, you can. This one's very, very challenging, because there are a lot of things happening. The very first thing is I. Layer I was deposited. Then B. Then F. That's easy, right? Because that's the law of superposition. So bottom to top. Okay. Well, then what happened? Then it looks like the layers were cut. They were cut. And then by this fault here. So the fault happened. And then it looks like what happened, there was an erosional event. All these layers were eroded. And you can tell by the squiggly line here, that's all an unconformity. And that's actually an event. An unconformity is an event because erosion is a process, so it counts. Then from that point, M was deposited on top of that, and then R, and then H. And again, because this has contact metamorphism on the top, R had to have been there in order for the contact metamorphism to happen. So IBF, fault, unconformity, M, R, and then the last thing is an intrusion, some kind of magma, and you can see all the contact metamorphism. And it cuts everything, right? This magma cuts through everything, so it must be the last thing that happened. Okay. And all of this has been relative dating. So all of these kind of putting things in order, trying to figure out the age of things relative to other things, that's all part of what's called relative dating. Determine the age of rocks relative to the surrounding rocks and other features in the area. That's what relative dating is. All right, that's it for today's lesson. There should be a Google form you have to fill out along with this lesson.